So here we have a definite integral from 0 to 5 of the absolute value of 2x minus 5 times dx. And so in order to evaluate a definite integral of an absolute value function, we're going to need to split it up into two separate integrals. Because if you remember what the graph looks like for absolute value functions, they are shaped like a V. And so we can solve this definite integral, which is calculating the area underneath this function from 0 to 5, by calculating the area under the negative side of the function from 0 to the vertex, and then calculating the area under the positive side of the function from the vertex to 5, which is the upper bound of the definite integral. And so all we have to do is determine what x value that vertex is located at. And in order to determine that, we just have to set the function inside the absolute value bars equal to 0 and solve for x. And so if we do that, we will have that 2x minus 5 is equal to 0. And so if we add 5 to both sides of the equation, that will cancel out with this negative 5, and we will have that 2x is equal to 5. And then if we divide both sides by 2, that will isolate x, and we will find that x is equal to 5 halves. And so the vertex of this absolute value function is located at x equals 5 halves. And so here's a more accurate representation of the graph of this function now that we know where the vertex is here at 5 halves, or 2.5, right? 5 divided by 2 would be equal to 2.5. And so what we want to do is split up this definite integral into two integrals, where the first integral calculates this area under the negative side from 0 to 5 halves, and the second integral will calculate the area under the positive side from 5 halves to 5. And so we will have that this definite integral is equal to the integral from 0 to 5 halves of negative 2x minus 5 times dx plus the integral from 5 halves to 5 of positive 2x minus 5 times dx. And so if we distribute this negative through this quantity, we will have negative 2x and positive 5. And so if we rewrite that, we will have negative 2x plus 5, and that will be multiplied by dx. All right, and so now we can integrate each term in each of these integrals, and we will have that this is equal to the integral of negative 2 times x. And so we're going to use the power rule of integration here. We're going to add 1 to the exponent of x and then divide by that new exponent. And so we will have negative 2 times x to the power of 1 plus 1, right? The current exponent is 1, so we will add 1 to that exponent of 1, and then we will divide by that new exponent of 1 plus 1. And then we will integrate 5, and the integral of any constant like 5 will just be equal to that constant times x. And so we'll have plus 5 times x, and all of that will be evaluated from 0 to 5 halves. Then we will add that to the integral of 2x, which, similar to negative 2x, we will add 1 to the exponent of x and then divide by that new exponent. So we will have 2 times x to the power of 1 plus 1 divided by 1 plus 1. And then we will add that to the integral of negative 5, which, once again, the integral of any constant is just that constant multiplied by x. And so we will have minus 5 times x, and all of that will be evaluated from 5 halves to 5. Okay, and so then if we simplify, 1 plus 1 is just equal to 2, and so this 2 in the denominator will cancel out with this 2 in the numerator, and so we'll have that this is equal to negative x squared plus 5x, and that is still going to be evaluated from 0 to 5 halves, and then we will simplify this term. Note that 1 plus 1 is equal to 2, and that will cancel out with this 2, and so we will have plus and then x squared minus 5x, and that will still be evaluated from 5 halves to 5. All right, and so if we clean up our work here, we can plug in our upper bound into this function, and then subtract plugging in our lower bound into the function, and we'll do the same thing for this evaluation as well. And so we'll have that this is equal to negative 5 halves squared plus 5 times 5 halves minus negative 0 squared plus 5 times 0. But note that 0 squared is 0, and then plus 5 times 0 would still be 0. And so we're really just subtracting 0. So I'll just write that. And then that will be added to 5 plugged into this function. So we'll have 5 squared minus 5 times 5. and then we will subtract, plugging in 5 halves into this expression, and so we will have 5 halves squared minus 5 times 5 halves. All right, and so then 5 squared is 25, and 2 squared is 4, so we will have that this is equal to negative 25 fourths, plus 5 times 5 halves will be 25 halves, and then we don't need to write that minus 0. That's not going to affect this value. But then we'll have plus 5 squared, which is 25. So we'll have plus 25. And then we have minus 5 times 5. So we'll have minus 25. And then we will subtract 5 halves squared, which will be 25 fourths, minus 5 times 5 halves, which will be 25 halves. Okay, and so if we clean up our work again, note that we have a positive 25 and a negative 25, and those will cancel each other out to just be 0. And so then we can work with the rest of our terms here. And we have negative 25 fourths plus 25 halves. And if we add those two fractions together, that will give us positive 25 fourths, right? Because 25 halves is the same as 50 fourths. And so if we subtract 25 of those 50 fourths, we will have 25 fourths. And so that will be equal to 25 fourths. And then we will subtract 25 fourths minus 25 halves. That's going to be negative 25 fourths. And so we are subtracting negative 25 fourths, which is the same as having 25 divided by 4 plus 25 divided by 4, which is equal to 25 halves. And that is the solution to this definite integral from 0 to 5 of the absolute value of 2x minus 5. All right, and so with that, that is the end of this problem. If you have any questions, feel free to leave those in the comments below. But if you don't have any questions and you found this video to be helpful or you enjoyed it, feel free to check out my channel where I have other calculus tutorials that you might find helpful. All right, but this is all I had for now, so I will see you next time.